Welcome everybody. Today I'm going to talk about the first few milliseconds of HTTPS. What I'm actually going to discuss is what's happening in the first few 200-ish milliseconds of an initial HTTPS connection. I'm going to give you some tips and hints on hardening your setup, give you some insights in new and upcoming technologies, and hopefully show you a thing or two that you probably did not know. So first of all, who's actually using HTTPS? Who has not raised their hands? I don't have hands. Okay, HTTPS is actually not a protocol. It's actually two protocols. HTTPS is HTTP on top of TLS. So today is not about HTTPS, it's about TLS. And TLS stands for Transport Layer Security. Anyone heard of that? Yeah. Most of you who haven't heard it have heard about the predecessor, which is Secure Socket Layer, SSL. Yeah, that rings a bell? Most likely. Okay, before I'm going to talk dive into HTTPS, I want to talk about SSL. And it's a short but very scary history on how it actually evolved. So back in the old days, 1994, who was born after 94? Only one? Everybody is older. Oh, we're old people here. All right. I feel old when I say 1994. Okay, there was SSL 1.0, and that is created by Netscape from the navigators. And that's actually vaporware, because it never saw the daylight. The thing is, it's a good thing compared to what came next, which is SSL 2.0, codename Not So Secure Socket Layer. Which is actually pretty bad, especially considering nowadays standards. And this was February 1995. So this is in the time that the internet, parents start to know about the thing called the internet, and with dial-up modems and everything. And this is the time that you start to upload pictures of cats and do some some commercial activities, and send over your credit card information. So there was need for doing things a little bit more secure. So SSL 2.0 is actually one of the first things that we could actually use on the World Wide Web. 1996, so a year later, came SSL 3.0. And finally, this is something that it's stable. It's okay-ish. It was good for the time. But it's actually something that we could use. 1996, so still in the period of discovering the internet. It took 3 years until we reached version SSL 3.1. And at this point, it wasn't Netscape anymore who created it, but it's handed over to an organization called the IETF. So the IETF, the task force, actually, built on top of what Netscape has made, SSL 3.0. But because it's something security and complex related, so what's the first thing you do? Rename the project. So instead of calling it SSL, they called it now TLS. And it's a simple minor release, considering SSL 3.0. So it's SSL 3.1, but they didn't call it SSL 3.1, they called it TLS 1.0. So TLS is basically SSL 3.1 or higher. So from 1999, nobody should talk about SSL. And everybody is still using SSL nowadays. So 18 years and counting. A whole lot of nothing happened until 2006. And there was a small minor update, TLS 1.1. Minor in the sense that it's not enough to call it TLS 2.0, but some new adjustments were made, and it's actually more secure right now. August 2008, so 2 years later again, we got TLS 1.2. And that's the final version we know of today. It's not completely, there's 1.3 coming on, but still TLS 1.2 is the last released version. 2008. Who was actually programming in 2008? Who wasn't programming in 2008? Was not. Okay, so you're newer than TLS 1.2. So 2008, so that's almost 9 years ago. So everybody is at least on TLS 1.1 and 1.2, right? Wrong. November 2013. These are the statistics. Only 18% and 20% uses TLS 1.1 and 1.2. The rest is lower. There are people still on SSL 2.0, you know, the 1996 stuff. People are still on that, 25.7% of the servers. But everybody else is in SSL 3.0 or TLS 1.2. They're always pretty close to each other, but that's basically because they're pretty much the same version, SSL 3.0 and TLS 1.1. Fortunately, a whole lot of stuff happened with SSL/TLS after November 2013. And it was actually a good thing. Things like Heartbleed and Poodle attack were actually good things because this happened. Just 4 years later, everybody is on TLS 1.1 and 1.2, almost everybody. TLS 1.0 is still there, but pretty much nobody is on SSL 3.0 anymore. And well, I highly doubt that the people who were on SSL 2.0 in November 2013 actually upgraded their protocol. So I think those servers just died in the meantime. So from 25 to pretty much nothing. To put it in schematics, you get something like this. Who knows what this drop is? A cliff. No. Poodle. Heartbeat, I think Heartbeat is somewhere like here. That didn't have effect. Poodle is the one that actually had a lot of effect. Poodle basically disable SSL 3.0 and get on with your daily life. And that, fortunately, that's what people did. This is the 2.0 line. Nobody cared, and nobody still cares. But this one is growing as well. So TLS 1.1 and 1.2 are actually growing. So that's a good thing. Today, I'm going to focus mostly on TLS 1.2. Everybody did their homework and read over the RFCs. Okay, please take out your notes. Nobody again. RFC 5246 basically talks about TLS 1.2, and TLS does 3 basic things. First of all, it's for authentication and exchanging information. It exchanges a key. This is important, a symmetric key to a public key system. And then it creates a tunnel with symmetric encryption where both sides of the tunnel use the same exchanged key. So there are 3 basic components: authentication, exchanging a key, and creating a tunnel with that key. If you put it in a network diagram, you get something like this. So there are a lot of round trips that are needed to actually set up a tunnel. That's a lot of work. So this is why SSL of TLS or SSL connections are a little bit more expensive than regular HTTP connections. What I'm going to do is actually have a network capture from some network traffic and show you what's happening in every of these round trips. For that, I'm actually using Wireshark. Is anyone familiar with Wireshark? Okay, excellent tool. So what I'm going to do is I'm going to start with basically the client hello part. The client hello part is where the client, the browser, connects to a server for the first time. Let's see if I can get this without blowing up my laptop. Sort of, kinda. Okay, can everyone see this? Okay, so what I did before this presentation, because I'm definitely not going to do this live, is I take a capture of an HTTPS connection between a server and a browser. And this is what you can see. So if I'm sniffing network traffic, you can see the same thing as I see here. So everything you see here is publicly available for basically the internet if you sniff it. So the first thing, what happens is there's a client hello package. And you see here that we have the internet protocol, the TCP protocol, and on top of that is the SSL, the secure socket layer. And it has a TLS record in there with some information. Now, there's a few things important. First of all, you see TLS 1.2 here, which basically says 030T. TLS 1.2 equals SSL 3.3. It's like, you know. But one of the important things is this random number. And that random number consists of 2 things. First of all, a date. Clock not properly set, I guess. Oh, this is the future. Welcome. and some random bytes. Those are just generated by your browser or by your client. Next up, most important things are the Cipher Suites. And you see here there's a list of 18 different suites. Now, don't care about the unknown one, but you see here TLS, ECDHE, a lot of things here with strange names, TLS, RSA, and that's a list. Basically, this is your client, your browser saying to the server, listen, we're going to communicate with an encryption, and these are all the encryptions that I know of in my preferred order. So it prefers the TLS, ECDHE, and then it goes down, and if you don't have it, we do this one, if you don't have it, do that one, etc., all the way down to the bottom. So how does that work? Let's go back again. So you get long strings like this, but it's actually quite simple to explain. So first of all, we have to break it down like this. So what happens here is that the TLS and the width you can skip, ECDHE underscore ECDSA. So the first part is the actual cipher, the encryption method we're going to use to exchange key information. We have to send over a key, and this is where we're going to send that key over with. Now, normally you have an accompanying protocol called, in this case, ECDSA, and that's actually for authenticating. So we can send over something encrypted, but the other protocol of the other encryption system is going to say, this is really the data that I have sent, and I proved to you that I sent it. Sometimes encryption methods can do that together. They can both exchange and both sign or authenticate. But if they can't, then you have two different protocols in this case. AES 128 GCM is the actual cipher and the length, the bit length, used for the communication in the tunnel. So it's what's a common misconception is that people think that an SSL certificate tells you how good or how strong an encryption is. But actually that's not the case. The strength of the encryption is decided between a client, a browser, and a server, a web server. And it can change between different. So I can connect with my browser to Google, and I can have a different encryption method used as I go to GitHub or to Microsoft or to any other website. So it's between the server and the client to tell you, to decide what kind of encryption you're going to use. So the last one here is actually a hash algorithm. It might as well have been MD5. There's still encryption there's still suites that use MD5 algorithms for message authenticating. So you can verify that somebody has sent over this package through TLS, but actually signed off that proven it's really me that has sent it, and it's not changed in any way. So this one is the same one. Basically, it is RSA that can do the exchange of the key and can do the authentication of the key, and it uses AES 265 for encryption in the tunnel, and use SHA 265 for the actual signing and the authentication of the message. Anyone has any idea what this does? Yeah, it's a valid cipher. Fortunately, not a lot of browsers actually support that. But if you do it, you would actually get a tunnel, but there's nothing encrypted in the tunnel. So it's like a transparent tunnel, normally for debugging purposes, but still it's a valid thing to have. So if you have a browser and you configure it in a way that you send, oh, I only want to talk TLS with TLS null with null null, there might be servers in the world that say, okay, sure, let's talk unencrypted, but still have like the green padlock up there. It's like, this is secure. I haven't tried it, but I'm definitely sure that there are servers out there that haven't set up their Cipher suites correctly. Which brings us to this. The client gives the cipher options, like the list of ciphers that we want, but the server ultimately decides on which cipher you're going to use. Normally it's the top one, but if the server does not understand the top one, it goes to the next one, to the next, etc., etc. This is why you should always configure your ciphers on your web server. Who of you has configured an HTTPS web server? Who of you have configured the ciphers? Okay, so there are people there that raise their hands. They configured ciphers, but not their web servers. It's strange. Okay. Always configure the ciphers, and it's pretty easy to do that because there's a website. Yes, there's a website, Cipher list, and it gives you a very strong cipher configuration for your web server. Could be Apache, could be Nginx, but could be other software as well, like IMAP and Postfix and all that kind of systems as well that use TLS for tunneling whatever they want to do. So take a look at. Don't copy over, just copy and paste the code over because you run into a lot of trouble, but just learn and read what it says and then configure your ciphers with that site. After you configured your ciphers, you can actually test if they are okay by using another site called SSL Labs, the SSL Test. And I normally try to run the test site of the conference website on SSL Test, so I did this as well. And it came out pretty good. So you can just type in the name of your website, and it just scans your whole website and checks to see if your TLS connection of your TLS SSL is in order, and if not, where the problems are. So in this case, phpconference.nl is pretty okay, which doesn't happen always on every conference, even security conferences where I was that didn't have HTTPS connection set up correctly, which is a bit of awkward. Okay, let's go back to this. So we got the Cipher Suites, and one thing we have here is a list of extensions, and those extensions are basically plugins into TLS. TLS by itself is a very simple protocol, but it uses extensions, and one of the extensions, actually the 0th extension, is called server name indication, SNI. This allows us to have multiple websites on HTTPS on a single IP. So this is a really important one nowadays, because if you don't, then you need an HTTPS connection, one IP per HTTPS connection, but you don't need to do that anymore because of this extension. Now, this extension actually is supported by pretty much every browser, server, and operating system nowadays, except IE6, Windows XP, BlackBerry, Android 2.6, and Java 2.x, and Java 1.6. So again, pretty much every decent browser, server, and operating system supports it. So there's no reason, like a few years ago, we can't use HTTPS because we don't have any IPs. It's not a problem anymore. Okay, so this is basically the client hello part. So the client has sent over a list of Cipher Suites and a random number. That's the most important things, plus the SNI for the server name. So the server does a server hello, because we also did a client hello. And the server hello looks a bit the same. So first of all, again, TLS 1.2 and a random number. So this is, again, a random number from the server. Again, everybody can see this information. If you are capturing the traffic, the NSA can just see these random numbers. It's not a problem. But here you see a Cipher Suite, not a list, but a Cipher Suite that's going to say, the server says, okay, I picked this Cipher Suite, this is where we're going to communicate with. In this case, TLS ECDHE number C030. And if you take a look in the Cipher Suite list, it was not the top one, but it was actually fourth one down. So that one, the server picked, I want that one, even though you have other options. Oh, let's go back. There. So that's basically what the server hello does. So random number again and picks the Cipher Suite. Next up, oh, hang on. Next up is the certificates, and I don't have a certificate here because it's cached. But normally it sent over a list of certificates, and the list of certificates, if I can take a look at it, hang on. go to my browser and I'm going to say no. Sorry about that, but it doesn't want to display my certificates. But basically what happens next is that the client I have it here. Yeah, I have it here. There we go. Okay, so what happens next? Sorry about that. What happened next is that the server sends over the server hello, but also a list of certificates. In this case, it sends 2 certificates. It sends a certificate for knoxlogic.nl, which is my company website, and it sends another certificate for Let's Encrypt, which is a certificate authority. Now, how many of you has heard about SSL certificates? Most of you have done that. Great. SSL certificates are, well, a bit of nasty work to be exactly, because it's quite strange to tell you what a certificate is, because if I go back again, there we go. What an SSL certificate is, I have to start what it is not. In this case, an SSL certificate is not an SSL certificate. It's actually an X509 certificate, but it's a more technical detail. But if you call it something, please call it TLS certificate, because SSL certificate died like 18 years ago. Also, it's not automatically secure. People think I have a certificate, so now I'm secure. Example, DiffieHellman. It's not automatically trustworthy. There are certificates where I say, if you got a certificate from there, then I don't know if I trust it. It's also not better than self-signed certificates. If a manager or somebody says, no, we have to buy certificates because they're more secure than the self-sign you are using on your daily work, that's BS. Because self-signed certificates are often even better and more secure than the certificates you can buy. They're also not cheap. Fortunately, Let's Encrypt has got rid of that one, because they are pretty cheap now, but not the domain, just for the domain validation. It's not for the organization and extended validated certificates. So what is an SSL certificate? Well, it's the best way. It's not a perfect way, but it's the best way to prove authenticity. Are you really the website I am talking to? It's also a way to bootstrap the encrypted communication. You know, we have to create a tunnel, and an SSL certificate has information to actually bootstrap that tunnel. It's also misleading. If I go to any SSL website or any website that sells SSL certificates, I can spot like 20 big misleading things straight away from the homepage. It's ridiculous. It's also too expensive, but again, Let's Encrypt has dealt with that. But often a certificate that's 10 times more, costs 10 times more than another certificate isn't automatically better. So, if I have a certificate for my domain or yourdomain.com, what actually happens is I can, that is signed. It's signed by something called an intermediate CA. And the intermediate CA, in this case Let's Encrypt, actually says, okay, I signed that, I put my signature on that and a stamp on that, and there's no way they can't be changed anymore. So what happens? It puts a sign on there by basically encrypting an MD5 hash or an hash from your domain certificate. So if you change something in your domain certificate, then the hash will not match anymore. And then it says, okay, your browser will say, well, there's something wrong with this certificate because the hash does not match up anymore. Now, the thing is, you cannot falsify that hash because you need information from the intermediate CA, which you don't have. The thing is, well, can we just change the intermediate CA certificate as well? Well, theoretically, you could. But then we have a root CA. And that root CA does the same thing. It will sign the intermediate CA. So if you're really paying attention, can't you change the root CA? Yes, you can do the same thing over and over and over and over and over again. But the thing is, there is something called implied trust. at one point in the chain, we have to trust the certificate that if we have that certificate, it is valid. We don't assume that it's tampered with in what way. So these certificates, these root certificates, are really important. These are coming from root certificate authorities, and they are built into your browser, into your operating system, and you will automatically trust them. So one thing you want to do is don't have a lot of root certificates in your system, right? Thing is, if you run this command, this small command, that actually gets all the root certificates from the Mozilla Security Store, which is the basic foundation for many systems that deals with TLS. So 20, about 20 would be a lot, right? The thing is, at this point is 181, and the number is still rising each and every day. So there are 181 companies out there who are in the business of selling as much certificates as possible on your system that you automatically trust, which I think is very, very scary, but unfortunately it's the only way right now to actually deal with that. So these X5 or 9 or SSL certificates are used to authenticate the server. The servers can actually do something else. They can ask clients to authenticate them as well. So it's not only a server that needs to authenticate. You can tell your web server to say, okay, I want to authenticate the client as well. There's no point in doing that on a web server because you don't care who your browser user are. But if you have an API, for instance, then it might make sense. If you have an API over HTTPS, you can say, okay, you can only connect to our API if you have our SSL certificate. So you don't have to create your own encryption and verification methods in PHP, for instance. It's already there on TLS, so why not use it? So at this point, we send over SSL certificates, we send over random numbers, and now we can send over our initial secret data. At this point, we are starting to send over data that nobody can do something with it. And this depends a bit on the type of encryption, the Cipher Suite that we're actually using. There are two main ways to do that. First of all, there's RSA, which is now a little bit outdated, and there's a next one called DiffieHellman. And RSA works like this. So a client generates a random key. So again, it's a random generated key, and it encrypts with the public key taken from the SSL certificate. In an SSL certificate, there's a public key, and you can encrypt data from it. The client sends that encrypted key over to this web server, and only the server can decrypt the key. So everybody can see that encrypted blob, but only the web server, the organization, can decrypt that information. This is how RSA works. It's a bit complicated with the math. Basically, it has two keys, a public key and a private key. So it doesn't matter that everybody can look at that encrypted information, but only the server can decrypt that information. On the other side, we have elliptic curve DiffieHellman ephemeral, which is the ECDHE. Basically, it does the same thing, but it doesn't use the key pair directly. It actually, the server generates a key pair. So it generates a public key, a private key. The server sent over the public key to the client with a signature to prove that it's really the key from that server. And for this, it uses the public key again from the SSL certificate. It's a bit complicated, but basically by using it this way, we can make sure that every time we make a connection, and every connection is encrypted, bootstrapped in another way. So you can only see it if you crack an encryption, for instance, then you can only crack one single transmission, and you can't see anything from the other transmission. This is different from RSA. RSA, if once it's cracked, you can see everything. In a DiffieHellman ephemeral, if you crack one, you can only see one. So it's much more secure in that way. Once both sides have a key pair, where the client sends over the public key to the server, then both the server and the client can calculate a secret. It's a bit hard, again, a lot of math to actually tell you how it works. But as soon as you send over that information, then both sides have the same key. So with RSA, both sides have the same key, and DiffieHellman, both sides have the same key. So as soon as we have the keys sent over in a secure way, we can generate secrets. So this is where the browser and the web server do the same thing. So first of all, we have the pre-master secret. That's the thing we send over from the client to the browser to the client. And we have the client random number and the server random number. So from this point, only the pre-master secret is sent over securely. The rest is global info, general information we send over with the packages. With this information, it hustles in a sort of mixer, and there comes out a master secret. And that master secret will be hustled as well, together with the server random number and again with the client random number, and it chops into a key buffer. And that key buffer is basically the holiest of the holiest. That's where your tunnel will function from. It will split up into 6 different sections: a client MAC, client key, client IV, a server MAC, server key, server IV. Now, notice that there's a client part and a server part. And that client part is used for the tunnel for the client side, from client to server, and the server part is used for the tunnel from the server to the client. So TLS does not build one tunnel, it builds 2 tunnels. So it's bidirectional traffic. That's also more secure, because what happens here is if somebody gets hold of the client key, then at least they can only decrypt the client to the server, but not the server to the client. You're probably pretty much effed by then, but if you aren't, at least you only can see half of the data, of half of the traffic, and not all of the traffic. This part, generating secrets and decrypting it yourself, you can do it in PHP as well. When I wrote this, I figured out that basically PHP is not capable of doing some things that I needed for this, meaning I'm the only one in the world who ever made something this in PHP, apparently. But it's still online. You can take a look at it on the TLS decoder. It will decode TLS traffic in PHP, so you can follow it all the way along. Okay, let's go back to the Wireshark. There we are. So you can see here we have a server key exchange. So in this point we're actually securing or sending over the information from the key. And then the server is done. It says server hello done. Basically, I'm done with everything I need to do. Then the client again comes over and the client says, okay, this is the information from my part, sending over the key exchange. And then we have a request called the change cipher spec. And the change cipher spec is pretty much, if I have it here, there's not much in there. But it basically says, okay, we've got all the information, we have the random numbers, we have the cipher, we have the encrypted key over. At this point, I'm not going to talk to you plain text anymore, but we're going to talk encrypted. So afterwards, there is no more plain text information from the client part. Well, the server has to say as well, okay, I'm done through, so I can start talking encrypted as well. So this is the change cipher spec from the server side. That's what we see here as well. So we have the client key exchange, the change cipher spec, then we're finished. And the last trip is the change cipher spec, and we're finished. Oh. Finally, at this point we have a tunnel. So at this point we can do HTTP if we are doing HTTPS, or we can do IMAP, or we can do whatever we want on top of TLS. The thing is, Wireshark cannot see, if I go back here, I cannot see any information what's stored here. This is just application data. It says TLS 1.2 application data, but it doesn't say anything what's there. It's encrypted. That's the whole point of TLS. I can't read it. But if I go back to my previous dump, here we are, there is a way to decode, to let Wireshark decode our traffic. What you can do is you can use the SSL Key Log file environment. If you do this on a Mac, if you set the environment SSL Key Log file to a file, then what would happen, certain browsers, at least Chrome and I think Firefox and I think a few others, will actually log information like your random numbers and your existing pre-master secret it stores that in a file so that Wireshark can read that file and actually encrypt that information for you. So you are basically telling any system, please decrypt my information from a browser. So I have put that up. If I take a look at, here we are. So every time I set up a connection to an HTTPS site, it stores that information in here. So in this case, this information is needed to go to certain websites with my SSL, this is needed to decrypt my SSL or HTTPS traffic. So this file is picked up by Wireshark, and I have to say to Wireshark in protocols all the way down to, of course it's not called TLS, but it's still called SSL because 18 years old. It's called TLS secret. And now you see it can actually decrypt that information. So you can see here it's a hypertext transfer protocol, and it gets the fav icon from a certain website, but that information is stored inside the encrypted application data. So with just a simple way, you can actually decrypt HTTPS traffic, which is fun if you do HTTPS APIs and you want to decode. So you don't need to do things like Charles proxy and send over certificates and everything. You can do that from your client laptop as well, just as easy. Okay, a lot of information, I know. The thing is, TLS has overhead in computation because it needs to encrypt and decrypt stuff, but it's definitely worth it. I don't think I have to convince anybody about using HTTPS anymore, fortunately. Google especially likes it nowadays with their rankings, I guess. Some Cipher Suites are better, but slower. This is why a server normally decides on which ciphers they want to use. We probably work on websites where that's not much of an issue, but if you have tens of thousands of servers and you are running really Facebook-like systems, then you want to make sure that you don't use too much processing power just for TLS. So you might have a quicker Cipher Suite, but less secure, maybe a little bit less secure. It's always a speed security compromise when you do things like that. You can try OpenSSL Speed, which actually benchmark all the different Cipher Suites that your system use to give you an information and give you an idea, benchmark on how fast every system is. But normally the ones we configure nowadays are more than enough. There are some attacks in TLS last few years. Still think that's a good thing. They create an RFC for just defining or summarizing the known attacks on TLS. So it gives you information. This is what happened. This is what you should do against it. Fortunately, there's TLS 1.3 in the making, but it's been in the making for a long time now. I don't know when it's released. It's about to be released, I guess. There's a few cool things. It's still in draft, but the 4 round trips you saw is actually going to be 1 round trip. So you can do a lot more in each round trip, meaning it will be quicker as well. There's even an initial 0 round trip, I think. I'm not sure if it's for handshakes, but on for resuming sessions. So that will be even faster, and especially when you do things mobile, that will actually make more sense because you don't need to do all the TCP connections anymore. Again, it dropped insecure features, so it will be not a real big overhead of, so this is why it's called 1.3 and not TLS 2.0. It's going to drop RSA for the Cipher Suite. You still use RSA, but in different ways. So that's a real good thing. I think this in combination with HTTP 2 in combination with TLS 1.3 will be a huge benefit for a lot of systems and a lot of websites. If you want to know more, what should I do? How should I do certain things considering SSL? Take a look at this website. It has the best practices. It tells you what to do and especially what not to do, because some things do not make sense and even weaken your security. Are there any questions? This one.
In the beginning, you showed us the various Cipher Suites.
Yes.
Which was generated by the client.
Yes.
Yeah. Does the server test the best preference from the server for which Cipher Suite to use, or does it just drop? This is the one I want.
Does the server decide? How does the server decide? Basically, that's your question. So the browser sends over a list of Cipher Suites in the preferred order, and the server has a certain list of their preferred order. If I'm gonna, hopefully this works, probably not because internet and conference. Now if you go to this website, what you can do is in Apache and in Nginx and others, you can actually say, this is the list of ciphers I'm actually supporting, and it will start with the strongest cipher, the one you want at the beginning. So the order in which you define the Cipher Suites on the server is important as well. There is an option that says, do not care about the order which the client sends the Cipher Suite, but always use the server order of preference. So that's an option that if you go to this website will show you as well. But basically it says, I don't care what the browser says, you do what I say. And that's the most secure way of how to deal with Cipher Suites. There's one there in the back.
Can you remove all Cipher Suites from your browser? Just giving the best, enforcing the best traffic or the best.
Can you remove ciphers from your browser?
Yes.
Probably not. Well, unless if you recompile your own browser. But every time you have an update on your browser, there will be updates as well. And basically, most browsers use the most secure, best ones at the top anyway nowadays. There are some weak browsers still out there that uses weak Cipher Suites, but it's up to you as a web server to decide, are we going to support like weak browsers? Or are we going to say, okay, listen, if you have a weak browser, you don't get to visit our site. So it's up to you as a company to deal with that. Okay, there's one.
Yeah, about it. TLS 1.0 is not as secure anymore as it's on its was.
Yes.
How can I find out which browsers are affected if I disable from my server?
How do I check affected browsers? The SSL Labs website, I showed you a link there as well. If you test your website, it will show you, it will test against all the different browsers there are. So you can actually see how your browser or how a browser connects to your website and what kind of Cipher Suite it will actually use. So you have a lot of information on that website about Cipher Suites and browsers connecting.
But you need to configure a site to serve like what you want to do with the rest.
Yes, yeah, okay. One more there? Yeah, don't. No. Yeah, yeah. A whole lot of BS. No, it literally sometimes is hot air what you are buying. You're buying reputation, often like a semantic certificate is probably just as good as a Komodo, but they are like 3 or 4 times more expensive. Sometimes you want to buy the name. There are all kinds of things that they will do or will not do, so it really depends on what you want. Normally, for smaller sites, you know, don't care sites, you don't need all that kind of things. So there's things like insurance, which is funny because if they have to pay out insurance, then they have to pay out not one person, but they have to pay out a whole lot of people. So what they're going to do is they bankrupt their company, so they don't have to pay out. So that's what you're basically buying a lot. So if you have somebody from an SSL company, he'll probably say, no, that's nonsense. So talk to them as well. But to me, it's not really necessary to do that. I think my computer and the beamer says it's time. If there are more questions, just come after me at the presentation. And with this, I would like to say thank you.